All right, welcome to session 12. This is the exciting session because we're going to finally put everything you've learned to use to create a big program. This is what I call the senior project. You're going to combine things to produce a useful application. Now, before we dive in and start creating this, I want to give a little warning, a little legal disclaimer. The program we're going to develop in this session is for educational use only. It is not guaranteed to be safe or able to handle all required situations safely. If you use any portion of this code in an actual application down the road, it's entirely your responsibility. SEW Eurodrive accepts no responsibility for injury or damages that may result. I have to say that because this is an educational application. It has not been designed like the applications that come with MoviTools Motion Studio to be bulletproof. It's simply a demonstration of concept. What you do with it down the road is up to you, but it's your responsibility whatever happens. So be aware of that. We're not trying to design something that you actually put into use. We're trying to design something to show you the process by which you would eventually develop something on your own. So that said, let's dive in. And we're going to approach this by introducing an extremely useful programming concept, something called state machines. If you're a programmer, you may have heard of state machines before. They're used in a lot of control applications. If you haven't and this is new to you, listen up. I'm going to give you a good explanation of what they are and how they work. So first of all, let's just define what a state machine is. It's a visual way of mapping out a control system's behavior in response to its inputs. Control systems, as you know, have inputs that govern how they behave, they have outputs that they change, and they make decisions along the way to manipulate information. A state machine is simply a way of diagramming on paper how a control system behaves, what it will do when its inputs change, what its outputs will do, how it's processing information. And I'm going to illustrate this with some very simple state machines, so hang in there if this sounds confusing. It's really not. It's actually a wonderful technique for designing control systems. First of all, let me give you another term here, and that is the term state. Control systems have conditions that they're in at a particular moment in time, usually a whole bunch of possible conditions. We call these states. And let me illustrate with a simple state machine that has just two states. We'll call this state A and state B. The program is doing one of two things at any given moment. It's either doing the things in state A or the things in state B. A state can be exited or entered as a consequence of events occurring on the inputs. Events are changes on the inputs. If an input changes, it is possible that the state machine will go from one state to another. So it exits the one, it enters the other. It doesn't always happen. Not every input causes a change of state, but in many cases, the state will change. So let me give you an illustration of that here. Let's say an input changes and you're currently in state A. You might exit it and enter state B. So we call that a transition when you move from one state to another. Remember, you always have a current state. You're never out of a state. You're always in one of these. And maybe then to get out of state B, a second input has to change to produce that exit from that state to move into the next, back into state A. Be aware that outputs can change in the states, but they don't cause transitions. Only the inputs cause transitions. The outputs may change in the states as the code within the state is executing, but they don't actually cause the transitions, so do be aware of that. Not all events cause transitions. Let's say, for example, that you have just transitioned from state B back into state A, so input number 2 has triggered a transition, and now you're in state A. What happens if input number 2 triggers again? Does it cause it to transition back into state B? Well, of course not. The state diagram doesn't show that as a legitimate way to exit the one state and go into the other. And so what happens is you just sort of exit the state and immediately re-enter it. In other words, it's kind of a do-nothing event. And the same thing would be true of state B. If you're currently in it and input number 1 triggers, well, you're not going to go back to state A. So we need to consider all the things that can happen with the inputs and what they will do in a given state. All right, that's the big picture of a state machine. If you found that confusing, you might want to rewatch this section again because you really do need to understand these. But if you think that made reasonable sense, forge ahead. I'm going to show you a real state machine that I guarantee you've interacted with at some time in your life. And that is an automatic toilet flushing valve. We've all encountered these. These are actually simple state machines. They're a really easy one to understand. We're all familiar with them. That's why I picked this sort of bizarre example. Let's talk about how these things work, and let's look at the state machine that describes their behavior. First of all, let's look at the inputs that are available, the things that cause events. There is a sensor on these, as you know, that detects when someone arrives and when someone departs. That triggers the flush. So that sensor is going to send 2 signals to the control system. It's going to say someone has just arrived or someone has just left. There's also that manual button that you can produce a flush just by pushing it, so that guarantees an immediate flush. And then there's actually a 4th input. It's a timer called a cycle timer. It controls how long the mechanism flushes. So the timer starts, and when it times out, it generates an event that indicates that it's done. There's also one output, and that is the valve control that opens or closes the valve to initiate the flush. That is it. It's a very simple system, just 4 inputs, 1 output. Now let's look at the states that are possible. Of course, there's the idle state. That's the state that you're in most of the time when nobody's there. It's just sitting there flashing the light on the front of the panel, and that's all. So we call that the idle state. There's also an in-use state, which means someone is using the facility. And there is a flush state where it's flushing the toilet by opening the valve for a period of time. So there are just 3 states for this machine. It's going to always be in one of them. It's never not in a state. State machines, by the way, always have something to keep track of the current state. And when you write your state machine for this project, you're going to have to set up some code that will always keep track of the current state. All right, let's work our way through a cycle. What happens? Well, we'll assume that we're in the idle state. Nobody's there, nothing's happening. And then what happens? Someone arrives. And so the sensor picks that up and it sends an arrived message. That causes a transition out of the idle state into the in-use state. So it transitions from one state to another, and while it's in there, it's going to monitor the sensors and decide what to do next. Now, these are the possibilities. The person could leave, which means the sensor will indicate the person left, walked away. All right, if that happens, it's going to exit the in-use state and go into the flush state to flush the toilet. Another possibility is that the person didn't depart but pushed the manual flush button. That too can exit the in-use state and transition to the flush state. So there are 2 ways to get out of in-use. Now, when you go into the flush state, the first thing that's going to happen is it's going to actuate the valve control to start flushing, and then it's going to start up the cycle timer because that determines how long it flushes. Maybe it flushes for 5 seconds or something like that. So it starts the timer, and what will happen is when the timer runs out, it will trigger a signal to go back to the idle state. So it will transition out of flush back into idle. Now, at this point, of course, the cycle can start over. It just depends what happened. If the person didn't actually leave, if the person pushed the manual button, the arrived sensor is going to trigger again, and it's going to go right back to in use. But if the person's actually gone, it will just sit and idle and wait. Okay, so that's the basic operation. Now, this state diagram is not complete. We have not considered every single possibility that could happen on a sensor. It is possible for sensors to be triggered in states that they normally don't control. We need to document those. We also need to just consider other possibilities, the unexpected, and make sure we've taken care of that as well. So let's consider all our possibilities here. Here's one of them. Let's say that the system is in the idle state and someone just walks up to it, doesn't sit down or anything, and pushes the manual button. Well, that is going to produce a flush, so we do have to consider that possibility that someone could just punch the manual button as they walk by. In that case, it'll go into the flush state, and it'll perform a cycle, and it will exit when the timer times out and goes back to idle. So that's a possibility we have to consider. Here's another one. Let's say that the person's arrived, we're in the in-use state, and that sensor keeps getting tripped because the person's right there, so of course it's going to keep triggering. Well, that's okay. That's just a sensor signal that we ignore. In other words, we exit in use and re-enter it immediately. That's not a problem. The same situation holds true during the flush cycle if the departed sensor goes off again. It just re-enters the flush cycle and basically is ignored. What if they push the manual button while it's flushing? Well, we want to ignore that because it's kind of pointless. If you're already flushing, then why worry about it? So again, that would just be one of those transitions that exits and comes right back in again. In other words, a do-nothing transition. And here's a third one. What if you arrive when it's flushing? Should you go into in-use? Well, no, you need to complete flushing first. So again, you ignore it until the timer exits that state, goes to idle, and then arrived will properly put you into in-use. So that is the complete system. We've documented every sensor possibility, every transition or every possible transition. We've covered all our bases. All right, that's our basic state machine. So I hope that made sense and kind of clarified it, because we're going to use state machines to describe what I call the senior project. And guess what? It is now time for the senior project. We are going to create a table positioning program. If you've ever used the application module available in MoviTools Motion Studio called Table Positioning, this is sort of a mini version of that program. It is by no means as complete or thorough, and as I've warned you before, it's not guaranteed to be properly safe, but it is something along the same lines. And you'll be able to develop that within just the course of this project. So let's go ahead and look at some of the program parameters. First of all, what is a table positioning program? If you've never used one before, does it have anything to do with moving tables around? And the answer is no, it does not. A table positioning program contains a list called a table, and I'm showing you one here. It has 4 rows. Each row contains a fixed location. So what the user does is pick a row in the table, and the drive moves to the position contained in that row. So if I picked row 2, for example, it would move to the position -391 millimeters. And this is absolute positioning based on the machine zero position that you determine when you reference. So the idea here is you have a list of fixed positions and you just move to those over and over and over. This would be used in some kind of an application where you always move to the same places in a sequence. Notice also that each row contains not just the position, but also the speed at which you're to position and a ramp time. And one row is called a teachable row. That means you can change the position. The way you would do this is you would jog the drive to a specific place, and then you would say teach, and it would store that location in the table. So there's one programmable spot in the table. All the others are fixed. You're going to use I/O signals to select the mode, the table row, and report program status. So this is kind of a binary control application. A PLC or some other controller would have to send the binary signals to control it, and it would have to read the digital outputs from the program to know what's going on. This is a very simple kind of application, very easy to implement, and easy to control with any kind of PLC or digital controller. As you've probably guessed, it needs to have a few other things besides positioning. It needs to be able to jog the drive so you can get it adjusted, and also to teach the teachable position, and you also need to be able to reference the drive. I think you realize you've actually created a lot of the code needed for a table positioning program already in your earlier programs. We're going to be using a lot of that code as you develop this. So you're not coding this all totally from scratch. You're building on your previous knowledge. Let's talk about the IOs, the modes, and the row select information. These are the inputs. We're using both the standard inputs and the option card inputs. Now, IPOS is only monitoring the standard inputs. We have controller, inhibit, enable, the reference cam, 2 limit switches, and the ability to reset faults. All the digital control of the application comes in on the option card. We're using DI10 and 11 to select the mode. DI12 is what we call the go signal. It triggers certain things to happen. DI13 and 14 control jogging, the direction you jog, and DI15 and 16 pick the row in the table that you're going to when you're positioning. These are our outputs. We're only using the option card outputs. DO12 indicates the motor status. When it's on, the motor's moving. When it's off, the motor isn't. DO13 signals that the application is ready. And then DO14, 15, 16, and 17 indicates which mode you're in. Are you jogging, positioning, referencing, or teaching? Very simple. So a PLC would monitor these and it would control the digital inputs to initiate operations. These are the modes. You go into jog mode if DI10 is 0 and DI11 is 0. You go into position if DI10 is 1 and DI11 is 0. You go into reference mode if DI10 is 0 and DI11 is 1. And if they're both on, you go into teach mode. So it's basically a 2-bit number comes in, 0, 1, 2, and 3 is what those are in decimal. And that determines what mode you're in. And also, I'm going to suggest the state you're in. Each one of these will be a state. And then finally, you select the row with DI15 and 16. Again, it's a 2-bit binary number that allows you to select one of 4 rows, 0, 1, 2, or 3. And that determines where to go when you're in position mode. That is it. This is very, very simple. Let me give you some details on the table. You're going to put it in non-volatile memory, so when you turn off the controller, the positions and speeds and ramps stay put. So here's where it's going to go. Row 0 is in H0, H1, and H2. Row 1 is H3, H4, and H5, and so on. So you're going to use the first variables in non-volatile memory. Now what that means is the user can edit this table using the All Variables tool, which automatically changes and reflashes non-volatile memory. That's how you set this table up using the All Variables tool. So nobody has to actually go into the code and make changes. They just go in and modify memory, the first 12 locations. Variable H9 is programmed by the teach mode. So when you go into teach mode and you trigger it, it will take the current position and put it in H9. And you should give H9 a realistic value before you've done your first teach. I usually set mine to 0, kind of the home position. You don't want to have some crazy position in there because that could cause trouble if the user has not actually done a teach yet. A few system details. You are going to store mechanical parameters also in non-volatile memory, like the jog speed you want to use, the roller diameter, and the gearbox ratio. Again, the user can do this with the All Variables tool. This allows the mechanics to be changed without touching the code. As you can guess, I do want you to use real units, specifically millimeters. And the program's going to convert between real units and increments. So all your positions are in millimeters. Speeds are in RPM down to 1/10 of an RPM, so 1 pseudo-decimal place, and ramps are in milliseconds. Very, very simple. Let's look at the state machine. This describes the entire program. It'll have a dispatcher state. This decides where to go. So this is kind of like the idle state. You'll have a jog state, a reference state, position state, and a teach state. And the inputs will determine which state you go into. Now, when the program starts, the first thing it has to do is start up an initialization, and then once it completes that, that's a one-time activity, it goes into the dispatcher state. And from there on, the program is going to cycle between different states. It will never be out of a state once it finishes initialization. The inputs control the state you're in. So for example, if the mode is 00, you enter the jog state by exiting dispatcher. If you change to mode 01, you're going to exit dispatcher, go into position. If the mode is 10, you exit dispatcher and go into reference. And if mode is 11, you exit dispatcher and go into teach. How do you exit these 4 states and get back to dispatcher? Well, there are 4 things that can cause an exit. The mode can change. If the mode changes, you immediately exit and go back to dispatcher. If enable gets turned off, go back to dispatcher immediately. If the drive gets inhibited, exit immediately and go back. And if one of the limit switches trips, go back. So these will all cause exits like this. Of course, you have to manipulate the outputs appropriately as you go along. For example, you may have to stop the motor or start it. You may have to turn lights on. There are a number of things that you may have to do in there, but that has nothing to do with exiting and entering the states. The states are basically a description of how the program behaves. So study this diagram carefully because this is kind of your roadmap for what you're developing. All right, let's look at some general guidelines for the program first. Then we're going to get into more specifics, and we're going to then actually write some code as well. I'd like you to use named constants for all the important numbers in your program. Named constants cost you nothing, so use them freely to improve readability. You should also break the program into individual user functions for the different operations. Basically, main should just handle initialization and dispatching. Beyond that, it really shouldn't do anything else. You need to use task 3 to perform background monitoring. You've done this before. It watches some of the inputs, it watches the status word, and I'd also like it to automatically update the motor status digital output. So when the motor's on, that bit is on. When the motor's off, the bit is off. You'll need to set up the positioning table in memory, and you'll need to do this with the All Variables tool. Don't forget to do this because you will be needing it. It does need to be in place. Also set up the mechanical parameters and jog speed table in memory with the All Variables tool as well. Just so we're on the same page, I'd like you to use these values in the table. So set up the positioning table as shown. Notice I've put a specific value in the teach location. I've put a 0 there. There should definitely be a known value that's legitimate in there. Of course, later when you teach the application, this value will change, but at this stage, you need at least have a position you could go to if you haven't done a teach operation yet. You can see the mechanical parameters here. Remember, speeds are down to 1/10 of an RPM, so there's a pseudo-decimal place. That means we're doing a jog speed of 200 RPM. We have a roller diameter of 50 millimeters, and we have a gear ratio of 4.25, which we represent with 2 pseudo-decimal places as 425. 2 final guidelines. Code the program in sections. Don't try to write it all at once. Set up the variables and the constants, set up the main and the initialization and the background task, then set up the dispatch code, that kind of thing. Do it piece by piece and certainly test as you go. All right, well, time to write our first part of this program. We're going to start with a new file, call it IPOSplus. It should basically be just the skeleton program because you're starting fresh. But do go back to your earlier programs. You can reuse a lot of the code that you wrote in there for this program. You really don't have to write this from scratch. You can do a lot of cutting and pasting. Let me give you the guidelines of what I'd like you to do for this section. We're obviously not doing the whole program at once. We will be doing it section by section. So here are your goals for this particular program part. First of all, set up your key variables and constants. Be sure to comment everything, remember, so everything is very clear and readable. Then, in the initialization, clear the option card outputs, that's DO10 through DO17. Calculate the positioning scale factor from H13 and 14. That's where the mechanical parameters are stored. Get all that done, then wait 5 seconds for the system to stabilize. Start up the background task. and then signal ready to the hypothetical PLC by turning the ready bit on. That will light up the ready light on the control box. At that point, you've completed initialization. You should enter the code for the dispatcher state. The dispatcher does the following things. It watches the mode bits to see which state it needs to enter. It also keeps an eye on controller, inhibit, enable, the limit switches, and the VFD fault status. You need to watch fault because when a limit switch trips, it also triggers a fault. And even after you put the limit switches back in the right state, until the fault is cleared, you still can't run. So the dispatcher needs to check these things. And only if the drive is allowed to run and the mode bit changes is it going to change states. I'd also like you to set up skeleton functions for the 4 states: jog, position, reference, and teach. You don't need to have anything in there but code to exit out of it when mode changes. You don't have to worry about controller, inhibit, enable, the limit switches, and the VFD fault status to exit out at this stage. Later you will. You will have to write some code for that, but right now, just set it up so that if the mode changes to something else, it will exit that function. And then test it all out and make sure it all works. So pause the video and go do it. Well, hope that went well for you. That was a sizable chunk of code, but it actually got you a long way down the road toward a completed program. Let's take a look at my program, and you can compare it with yours and see if there was anything you forgot to do, or if you had any problems. Maybe this will help you see how you can resolve those. So let's take a look. Okay, well, let's take a look at my program here. First of all, I'm going to go to the All Variables window, just to show you that I've set up my table. I went in there and I just entered these values one after the other. They automatically get flashed into memory. We have our positioning values and we have our mechanical values. Everything's set up correctly. It's important not to forget this. You're going to need this table fairly soon. Let's look at the code now. We'll start with variables and constants. A lot of these should be familiar. Of course, we have pi in the encoder resolution. This is just used for the mechanical computations. Down here, we have all our output bits on the option card I/O. These are just the bit numbers. These will reflect the status and communicate back to the imaginary PLC what's happening. These bits are important here. I'm looking at the option inputs and using masking and shifting to isolate the various control bits, the 2 mode bits, the single go bit, the 2 jog bits that indicate direction, and the 2 position bits that indicate which row in the table to access. Notice I'm using option inputs. That is a variable that is updated by the background task. It just sits there and watches the inputs, passes them back in that variable, and then these defines here include the necessary code to do the masking and shifting. Moving on, we have our different modes: jog mode, position mode, reference mode, and teach mode. These are the numbers that the mode bits will change to indicate that we want to change to those particular states. I've also created constants for all the states so we can keep track of which state we're in. We have the dispatch state, the jog, position, reference, and teach. And then lastly, we have named variables for those 3 non-volatile variables that contain the mechanical parameters and the jog speed. This is the best way to access these. We can access them now by name rather than H number. This should look familiar. This is from our earlier program that uses background task 3 to report status. These are just variables that will be updated automatically. There is one change, however. I've added one additional status variable we didn't have before that monitors the limit switches. Remember, both limit switches are supposed to be on for the drive to operate. If either one goes off or both go off, you'll get a fault and the drive will stop. What this single value will indicate is if a limit switch is tripped. If a limit switch is tripped, we'll get a true. If the limit switches are in normal operating condition, we'll get a false. All right, so we're going to have to update our background task code to update the limit switch variable. We then have our mechanical parameter computation variables, nothing new there either, and then one more variable called state that we're just keeping track of the current state we're in. We're going to add other variables as we go along, but that's enough for this phase of the program. All right, now we have our main code right here. Let's look at the initialization. That's this code here. First of all, we turn all the option card outputs off. We do our mechanical calculations to work out the positioning scale factor. We pause 5 seconds for the system to stabilize. Then we start up background task number 3. And finally, we turn the ready bit on to signal the PLC that the application is ready to go. Pretty simple, very much like many of your earlier programs. Now, before we look at the while loop and the dispatcher code, we're going to jump down to the end and look at background task 3's function because it has changed a little bit. It contains code that you've seen before where it monitors the controller inhibit and the enable bit. But here is some code for monitoring the limit switches. Limit switches are DI4 and 5. What we need to do is isolate them, mask them, shift them. If both limit switches are on, we should have a 1, 1, which in decimal is 3. That's the equivalent of binary 1, 1. If both those bits are on, then this if statement will set limit switch to false, which means the limit switches are happy. Otherwise, if either bit is off or they're both off, then we'll set limit switch to true, which means we have a limit switch trip. So that is the one change. We do that with an if statement. Everything else is pretty much what you've seen until we get to the very end here. And this is new code. It updates the motor status bit. What it does, it watches the stopped bit in status word. If the drive is stopped, it means the motor's off. So we say if it's not stopped, turn on the motor bit using bit set. But if it is stopped, then clear that bit, turn it off. That will give us an active report of what the motor is doing. That's all we have to do in background task 3. Pretty much what you're used to, a few new things, but pretty straightforward. Now let's go up to our dispatcher code. It takes place in the infinite while loop in main, right here. First thing it does, it sets the state variable to dispatch because that's where it begins. And then it checks to figure out if the drive is permitted to run. In other words, can it transition to one of the other 4 states? To do this, we use an if statement and we look at inhibited, enabled, limit switch, and fault. We say if not inhibited and enabled and not limit switch and not fault, then you can go ahead and change states if you want. But if any one of those conditions or multiple conditions are true, it will not allow you to change state. It will just stick in the dispatch mode. Notice we had to monitor fault as well as limit switch because when a limit switch trips, it trips a fault. And until you clear that fault, the drive can't run. So we need to watch that as well. Now, if we get past those 4 conditions, we have a switch statement that looks at the mode bits, and if the mode bits equal jog mode, then we call the jog function. If they equal position mode, we call the position function. If they equal reference mode, we call the reference function, and if they equal teach mode, we call the teach function. That is it. That is all we put in main, just the initialization and the dispatcher code. Finally, we have the skeletons of our 4 state functions. We have the jog function right here. Every one of these does basically the same thing at this point. It changes the state, in this case to jog. It checks to see if the mode bits are still jog mode. If they are, it just stays in that while loop and jogs. The minute the mode changes, then you exit the while and change back to the dispatch state and exit back to main. All of these do the same thing. So notice position does the same thing, reference, and teach. The only difference at this stage is the mode values and the state values. Eventually, we will add some code to these to detect things like controller inhibit, enable going away, limit switch trip, and faults. And if that happens, then we'll jump out as well. But we didn't have to do it at this stage. All right, so nothing terribly complicated. This is pretty straightforward. It's a lot of code, but nothing hard. Let's compile it and just give it a quick test. So we're going to run it. And then the first thing I'd like to do is go to the All Variables window again and just make sure that some of the initialization took place correctly. I need to find my regular variables here. There they are. So we have all our status variables. We also can see our circumference is computed, encoder scale has position scale. I did check those on a calculator just to make sure that they're correct, and they are. I also see that state is changed to state number 1. That's actually jog mode because the 2 mode bit switches are off. That gives a 0, 0, and that goes to the jog state. So we're going to do a little testing here just by looking at the variable window to see if things work as we expect. I have my control box here. I'm going to just check a few things out. Let me take controller inhibited away to make sure that changes. You can see it does. That's fine. I'll turn it back on. I'll take enable away. That changes. Now let's triple limit switch. I'll turn DI4 off. Now that should make limit switch change to 1, and also the fault bit should change to 1, and it has. I'm going to put the limit switch back on. Notice the limit switch variable changes back to 0, but fault is still on. I've got to clear the fault, and I'm going to do that by toggling DI7, which is assigned to clearing faults, and you can see fault is gone. That looks good. I can see that my motor stopped bit is 1. That means the motor isn't running, so my motor status light DO12 should be off, and I look at my control box and it is. That's good. Now let's go ahead and change a few states. I'm going to change my mode bits DI10 and DI11 to see if the state changes. I'll go to the position mode by turning on DI10, and you can see state change to 2. Now I'm going to make sure it exits by turning it off. That'll go back to jog mode. Went back to 1. Okay, so far so good. I'll go into reference mode by turning on DI11. That goes to 3. Let's transition now to teach mode by turning DI10 on as well. That should go to state number 4, and it does. I'll turn them both off. We go back to jog mode. Looks like that's running as well. So everything so far seems pretty good. I'll check DO13, that's the ready light. It is on. That's good. Therefore, it appears we have successfully initialized, computed our positioning values, started the background task. It is working correctly. Our motor status and our ready status are good. Our dispatcher code is working, and we're able to move in and out of all 4 states. That's all our code has to do at this point, so everything should be good. If your code does all this, then great, you're ready to move on, but if not, of course, you probably want to go and fix it before you move forward. All right, well, let's forge ahead. We've gotten a good chunk of our program written, but we need to keep moving, so we're going to add some more to our existing file IPOSplus. First of all, we're going to complete the jog state function. You've already created the skeleton code for it. We're just going to add to that. You'll need to do the following things. You should set the motor speed to the jog value. Remember, that's contained in variable h12, and I'd like you to use just a hard-coded 0.5 second ramp, 500 milliseconds. By the way, I would suggest you do that in the initialization part of your code, since you only have to do it once, and that variable never gets reread at any other point during the program, so I'd do it there. Now in the jog function itself, here's the way it should behave. If the jog minus switch is on, that's DI13, the drive should turn counterclockwise. If the jog plus, which is DI14, is on, it should run clockwise. And if both bits are either on or off, the drive should not run. And if it is running, it should halt immediately. Whenever the drive is jogging, the jog status indicator, which is DO14, should be on to reflect that, and it, of course, should go off when the drive is still. These are the conditions that will exit the jog state, halt the motor, and re-enter the dispatcher state. The mode changes to something other than jog. Controller inhibit is activated. Enable is removed, or a limit switch trips, which causes a fault. Any of those should exit. All right, so that's the jog function, and you can obviously reuse some of the code that you've written in the past in some of those jogging activities to implement that. Moving on, I'd also like you to complete the reference state function. Please double check that referencing mode is set to 1 in the parameter tree. That's the one we expect to use here. And here's the way it should work. First of all, it should wait for the go switch, which is DI12, to turn on. As soon as that happens, you should turn the reference status indicator, DO16, on and start the referencing operation. Now, if referencing completes normally, turn off the reference status indicator and then wait for the go bit to turn off. You don't want that to just re-trigger referencing again. If you turn go back on again, then referencing should happen again. Now, these are the conditions you need to exit the reference state, and if the motor is running, to halt it and reset the referencing operation, as well as turn off the reference status indicator. And then, of course, re-enter the dispatcher state. So these are the conditions that will cause that to happen. A mode change, you change out of reference to something else. Controller inhibit gets activated, enable gets removed, or a limit switch that causes a fault occurs. Do remember, in referencing mode 1, limit switches do not always cause faults, so you need to accommodate that. 2 handy tips that might make things go a little better. Use access stop with the constant ASP stop, that's positioning stop, to halt all positioning operations. That includes jogging, because those really are just modified positioning operations. Secondly, use the access stop with the ASR stop, that's the rapid stop, to halt referencing. All right. Go ahead, pause the video, and write some code. All right, well, let's see how you did. We'll take a look at my code, and you can compare it to yours and maybe get anything unstuck that was troubling you. So let's take a look. Okay, well, let's take a look at my code and see what I added. First of all, I did add 2 more variables right here. I just declared them as longs and called them var1 and var2. These are for the setSys function. We use that to set ramps and speeds, which we have to do for jogging. Therefore, I've created these. And I also added that code to set up my jogging speed and ramps. This is just a call to setSys. I do that twice. I put it in initialization because I only have to do it once. All right, nothing more beyond that. Now we move on to our jogging code. So here it is. It's actually pretty simple and straightforward. Now, one of the things I had to do is expand the exit condition. Remember, before, the only thing that caused us to exit jog and go back to dispatch was the mode changing out of jog. I expanded that now to include controller inhibit, loss of enable, limit switch trip, and fault. As long as not one of those conditions is true and the mode stays jog, of course, the while loop keeps cycling. But if any one of those things happens, we exit the jog state. And what happens there is we do 3 things. We do an access stop with pstop. We turn off the jog status indicator, and we return to the dispatch state. That will happen if any of those things happen. Mode changes, controller inhibit trips, enable goes away, limit switch happens, or a fault. Now, if those things do not cause an exit, we go into a switch statement, and it looks at the 2 jog bits and decides what to do. Now, if both those jog bits are off, it immediately does an access stop and turns the jog indicator off. If both those bits are on, which is an impossibility, you can't jog both directions at once, same thing, does a p-stop, turns the jog bit off. However, if just one bit is on, it rotates clockwise or counterclockwise, and it does it with that tail chasing technique, where it simply takes the motor position and either adds or subtracts 1 rotation from it, and then feeds that into target POS. This is the counterclockwise code, and this is the clockwise code here. All right, really straightforward stuff. Let's go ahead and give this a quick test. We're going to compile our code. and run it. Take our control box and see what happens. Let me bring up my all variables window because we kind of want to watch what's happening. So let me roll down to my variables. Here they are. Since we're going to use the all variables window quite a bit as we test our code, let me give you a little warning about it. Remember what I've said in the past, it doesn't always update quite in real time, so sometimes when I'm talking about the code, you'll notice the variables window is lagging behind a little bit, or sometimes if I flip a switch really fast on and off, it may not even catch it at all. So don't let that throw you, just a heads up. Okay, so right now everything is legal to run. Controller inhibit has been turned to the on condition, enables on, no limit switches, no faults. You can see that state is 1. That is the jog state. So let's try to jog. I'll go ahead and turn one of the jog bits on. We'll turn on DI13, and the motor is rotating counterclockwise. All right, turn DI13 off, drive stops. Let's try DI14, and we've got clockwise rotation, so that works. Let's turn both on just to see if it halts. And it definitely does. I'll turn one off now, and it's spinning again. Let's turn them both off, see if it stops. Yes, indeed it does. It appears that that functionality is good. Now let's go ahead and try some of the abrupt stops. Let me get the drive running again, and I'll remove controller inhibit, and it stopped abruptly, and you can see the state went to 0, which is dispatch, which it's supposed to do. If I turn controller inhibit back on, then dispatch should redispatch it to the jog state because the mode is still set to jog, and since that jog switch is on, we should see the drive immediately resume operation. Let's confirm that. And yes, indeed, that works. Let's check enable. I'll turn that on. That also stops the drive. Let me turn it back on. Drive should resume normal operation. And it does. Let's triple limit switch. That indeed stopped the drive. And of course, I have a fault as well. I'm going to turn the limit switch back on now. Now the limit switch is cleared, but the drive is still in dispatch. That's because the fault isn't clear yet. I have to clear the fault. I'll toggle DI7, and that got rid of the fault. The drive resumed operation. Let me check the other limit switch just for thoroughness. That too stopped the drive and faulted it. Let me turn it back on and reset. Okay. One last check. We need to make sure that if we change the mode, we drop out of jogging. Let's try that. We'll change the mode, and yes, it works. Okay, well, it looks like everything is working. All the exit conditions work. The drive jogs correctly. We're in good shape. Okay, let's talk our way now through the referencing code. As you can see, I've fleshed it out from the skeleton state. The first thing I'd like to point out is I have expanded the conditions that exit the state. Originally, of course, the only way you could get out is by changing the mode from reference mode to something else. Now I've added some extra conditions, so if any one of these is true, it can cause the while loop to exit. But as long as not one of those exit conditions is true, the while loop will just keep looping. So notice I have controller inhibit, the enable signal, the limit switch, and fault. As long as not one of those things is messing up, and as long as the mode bit stays to reference mode, the while loop keeps going. Now, the next thing we do is we wait for the go bit. We wait for the switch, DI12, connected to that bit to turn on, and that's the signal for referencing to start. So we just do a simple if statement. Of course, if the go bit is off, the if statement just falls through and the while loop just keeps circling. So it just keeps running through that if statement over and over until it's true. Now, as soon as it is true, the very first thing we do is we turn the reference status indicator on to signal the PLC that referencing has commenced. We then start referencing by issuing a go0 function call. Notice we're using the unconditional no wait form, and we are using the 0 pulse. That will initiate referencing. Then, this should be familiar, we've done this before, you check the referenced variable. Remember, this is monitoring the status word bit IPOS referenced, and what will happen is it could well be 1 at the beginning here, but it should change to 0 as soon as referencing starts. So we sit here and wait for it to change from 1 to 0. That usually happens very, very quickly, and then we're formally in referencing. Now, what's happening while we're in referencing, a number of different things can happen. So we've got this monster while loop that's just going to sit and spin. Normally what it's doing, it's watching the reference bit to see if referencing is completed successfully. And you notice that is in there. Notice also I've had to pack everything together with no white space. It's because this line is so frighteningly long, so it's not very readable, unfortunately. But notice we have not referenced in there, so as long as it's not referenced, we keep looping. But when we successfully reference, we'll drop out of the while loop. We also have the early exit conditions. We check the mode bits, so if you change to a different mode, it will terminate the referencing operation and drop out. Controller inhibit can do that, so can enable, so can a limit switch touch, and a fault. Any one of those things happens, the while loop ends. Once that happens, the first thing we need to do is figure out, why did the while loop end? Did it end because referencing completed correctly, or did we do an early exit? Well, if we did an early exit, then this if statement will catch it, because it checks for every possibility. It checks for a mode bit change, it checks for not being referenced, it checks for controller inhibited, not enabled, a limit switch touch, or a fault. If any one of those things happen, that was an early exit, and it's going to do 3 things. It's going to do a rapid stop by calling the access stop function. It's going to reset referencing to say it never happened. And it's going to then re-enable the access, because after a rapid stop, you have to re-enable the access to move again. It will do those 3 things and then move on. At this point, regardless of the reason, whether it was completed referencing or an early exit, we come down to this point in the code and we turn off the reference bit to signal the PLC that referencing either completed or got terminated early. For whatever reason, we're no longer referencing. And then finally, we need to do one more thing. We need to make sure that go switch gets turned off. So we watch the go bit, and if the go bit goes off, we drop out of the while loop, and that's it. I also, though, have all the early exit conditions covered as well. I'm checking my mode bits, controller inhibit, enabled, limit switch, and fault, because if one of those things happened, we need to know about that too. If nothing like that happened and we just completed referencing normally, as soon as I turn off the go bit, the while loop exits and then the main while loop takes over. It doesn't actually exit the reference state, it just stays in it, and if I want, I could hit the go bit again and re-reference. That's perfectly fine. But if I did an early exit, on the other hand, this while loop is going to drop out and it's going to drop me back to dispatch. It'll move me back to the dispatch state. So all my bases are covered. Yes, we had to check an awful lot of things. The code wasn't that complicated, but it had tons of things to look over. But I believe we've covered all these, and so we're good now, and we can compile our code. And it compiles fine, and then run it, and then bring up the variable watch window so we can see what's going on. So we'll go back to our variables here. Okay, so now we're ready to try things out. You can see from state that we're already in the reference condition because I flipped the mode switches to put me in referencing mode. Let's go ahead and just do a plain normal referencing and make sure it works. I'll turn the go bit on and we should see what happens. All right, we are clearly referencing. I'll go ahead and trip the cam. And you can see that we did succeed with that. We didn't go right back into referencing again, even though I've left the go bit on, so I'm going to turn it off and see if I can trigger it again. I'm going to turn it on once more. Okay, and that triggered referencing again. So clearly it is checking correctly. Let's complete referencing once more. There we go. All right, now we need to check the early exit conditions, and we have a number of them, so we'll have to check them one by one. We'll start with controller inhibit. Let's trip the go bit. And now I'm going to hit controller inhibit, and it did indeed stop it. And it did go back to the dispatch state, which is what it's supposed to do. Now I'm going to turn controller inhibit back on, and what will happen is dispatch should drop me back into referencing once more. And it does. Let me go ahead and trigger referencing once more. And now I'm going to remove enable. Once again, that caused things to stop, and you can see we went back to dispatch. Let me put enable back. Now let's go ahead and trip a limit switch. I'll trip the right limit switch first, and that certainly caused a fault. So even though I've just turned the limit switch back on, nothing has started up again. That's because I have to clear the fault. Let me clear the fault with DI07. One more thing I have to try here. I need to change my mode while I'm in the middle of a referencing operation to see if it escapes. Let's do that. I'll go back to jog mode. And it does indeed stop. It's now sitting in jog mode. Let me go back to referencing mode. Well, it appears that everything seems to be working. So this was a rather complex bit of code with a lot of things to test, but I think we're in good shape. All right, well, now we're finally getting into the meat of the program, and that is positioning. So our next task, as you can probably guess, is to write the positioning code. Of course, we're using our existing program. So here are the requirements for the positioning code. You're going to go into the position state function and flesh it out. First of all, you need to wait for the go bit, which is DI12, to turn on. That signals positioning should start. As soon as the go bit goes on, turn the POS status indicator, which is DO15, on. This signals the PLC that positioning is started. Then you need to look at bits DI15 and 16 because that indicates the table row, 0 through 3. So you need to retrieve the correct row, get the position. Of course, you'll have to convert it to increments because it's in millimeters. As well, you'll have to get the speed and the ramp and program those, and then of course start positioning using those row values to control the drive. Now, if the positioning operation completes normally, in other words, it arrives at the destination, turn off the POS status indicator to signal the PLC that it's finished, and then wait for the go bit to turn off. If positioning does complete normally, you want to stay in the position function. You could pick another row and then trigger the go bit again. However, you can exit the position state, and you can do it under a variety of conditions, but here's what should happen when you request exiting the position state. The motor, if it's running, should be halted. You should turn off the POS status indicator and re-enter the dispatcher state. Now, what can exit the position state, either when you're in motion or when you're just sitting idle? Well, of course, the mode can change to a different mode. But you can also do the sudden stops. For example, you could inhibit the controller, you could remove enable, or you could have a limit switch trip along with the associated fault. Those are all conditions that can exit, and they can happen at any time when you're in motion or when you're just sitting. All right, pretty straightforward. This is a fairly sophisticated piece of code, so I think you need a little handy tip here to help you out. Let me give you one. I suggest doing a wait 100. Wait 100 milliseconds, about 1/10 of a second, after the positioning function call. This gives the status bits enough time to update and give you really an accurate picture of the drive status. If you do this, I think things will go a little better. And with that said, go ahead and do it. All right, well, hopefully your positioning code worked well and you were going to the different positions reliably. So let's compare my code to yours and you can see how you did. Okay, let's take a look at the code we've created and then we'll give it a test. First of all, we did add a few more variables. These are named variables that we've added. This is our positioning table. So notice I've associated a name with each of the H variables that contain the position rows. POS 0, speed 0, ramp 0, that's the first row. POS 1, speed 1, ramp 1, the second, and so forth. This just makes it a little easier and more readable again to address our positioning table stored in memory. I'd like to point out something that the sharp-eyed amongst you may have noticed. I made a change in a variable name. You notice we have a variable here called incs, which stands for increments. That used to be called position in an earlier version of this code. I decided I wanted to use position for something else that I'm going to add in this section. In fact, I'll be talking about it in just a second. So I renamed this variable incs. So don't let that throw you if you've been following my code closely. Good. Continuing on down, I've added 3 more variables, position, speed, and ramp. What I'm going to do is when I access my table, I'm going to take whatever row I'm going to use and I'm going to put its values into position, speed, and ramp here. And then those will be used for the actual setting the speed and the ramp and doing the positioning operation. So now we can just go ahead and move forward to our positioning code. Again, we've fleshed this out a little bit. First of all, I've set up the exit conditions. Remember before we just had it set up so if you changed out of position mode, it would go back to the dispatcher. Now it's checking that the mode stays in position mode. It confirms we're not inhibited, we are enabled, we don't have a limit switch trip, and we don't have a fault. As long as those conditions are all true, we stay in this state, the position state, and we go forward in the code. Now the first thing we do is we watch for the go bit, because we want the go bit to go on. So until the go bit goes on, nothing happens. We just keep looping in the while loop. But as soon as the go bit goes on, we do a bit set and turn on the POS bit, which turns on the status indicator. And of course that signals back to the PLC that positioning is started. The next thing we have to do is retrieve the correct row. Now POS bits, that 2-bit number, indicates which row we want to use for our positioning. So we have a switch statement. We switch on that, and then we have 4 cases. We'll just look at the first one here. If it happens to be 0, both bits are off. That's our first row. And it says use POS 0, speed 0, and ramp 0. And take those values and shove them into position, speed, and ramp, and then break out of the switch statement. We do exactly the same thing for the other rows, just using different variables. Then we come down here, and the first thing we have to do is program the speeds and ramps. So we put speed in var1 and var2. We're using the same speed for each direction. We call setsys. We set the positioning speed. Then we do the same thing with the ramp. We use the same ramp both up and down, so we put ramp in var1 and var2. Again, we call setsys and do a POS ramp as the parameter we're changing. So far, so good. We then have to compute the number of increments we wish to move. So we take our position, multiply it by the scale factor, which converts from millimeters to increments, and then we divide by 100 to take out those pseudo decimal places. That gives us the number of increments to go. And then finally, we start positioning with the Go ABS. We do it no wait. And we do a 100 millisecond wait right after that, just to give everything time to update. What will happen at this point, of course, is the motor will start spinning. Now we have to watch for conditions to exit out of positioning mode. And we have basically 2 sets of conditions that can force us to exit. The first, of course, is arriving at the destination position. In other words, the positioning operation completes. But we can then also have early exits. Now, this could happen if the mode bit changed and put us in a different mode, if controller inhibited activated, if enable got removed, if we touched a limit switch and caused a fault. Therefore, what we do while it's doing the positioning is we get into a while loop. Now, this is pretty much the same thing we did in referencing mode. We watch the mode bits for a mode change. We watch the in position variable to see if we've arrived. And then we watch controller inhibited, enabled, the limit switches, and fault. As long as we're not in position and we haven't forced an early exit, we just sit here waiting in the while loop. Eventually, one of 2 things will happen. Either we'll arrive and jump out of the while loop, or we'll do one of the early exit situations and jump out of the while loop. When we jump out, the first thing we have to do is find out why did we jump out. So what we do here is we do an if statement to see if we have an early exit. This checks for all the early exit conditions. If the mode bit doesn't equal the POS mode, or we're not in position, or we're inhibited, or we're not enabled, or we've touched a limit switch, or we have a fault. Any one of those will indicate an early exit. And we do just one thing here, so we didn't even need curly braces since it was just a single thing. We do an access stop using pstop. That's the normal positioning stop, and that is all. So we shut off the motor. Now, the next thing we do happens if we did an early stop or we just arrived. We turn off POS bit to say we're no longer positioning. So we do a bit clear on that. So an early exit will turn it off, and just a normal arrive at position will do that. Now, the last thing we do is we wait for the go bit to go off. That would be normally what would happen perhaps if we've arrived at the correct position, but it could have been left on and we tried to do an early exit as well. So we're looking at everything again. We're considering, well, if the go bit's on and we're still in positioning mode and we're not inhibited and we're enabled and we didn't touch a limit switch and we're not in a fault, in other words, probably the go bit is sticking us here, we just sit and spin. Now, as soon as we turn that go bit off, it'll exit the while loop, it'll go back, and we could do another positioning operation if we want. However, if we did an early exit by changing our mode or controller inhibiting or removing enable, or touching a limit switch, or getting a fault, this while loop will exit, and what will happen then is it'll go back to the beginning, to the main while loop, and that one will exit too. If we had a normal position, that wouldn't happen. It would allow us to go back in and do another positioning. But if we have an early exit, it'll jump out of here, go back, change to the dispatch state, and exit the function. Okay, so again, fairly complicated code, mostly because we have all those exit conditions we have to watch out for. But not too bad on the whole. Okay, so we need to test our code out now. We need to compile this, and we need to do some positioning operations. Let's compile our code. No problems there. We'll run it. And let's get our all variables window up here for a second. We are going to want to watch it. Now, I'm going to pick two locations to jump back and forth between when we're testing. I'm going to use position 1, which is 2003 millimeters, and position 2, which is negative 391. That allows us to do a fairly big sweep back and forth, so we have time to watch how it behaves and test the early exit conditions. That's what I'm going to do, so I'll be setting my position bits to 1 and then 2. Okay, now let's go down to the main batch of variables. There we go. And I'm going to take my control box, and everything is enabled and ready to go. The first thing I'm going to do is reference my drive because I want to be sure I've got a known 0. So I'm going to put it in referencing mode, and I'm going to trigger the go bit and then hit the cam. So here we go. And I'm now referenced. All right, I didn't show you that. You've seen me reference many times. So we now have a known 0 position. So let's go ahead and get ready to try out a position. I'm going to put it in position mode by setting the mode switch to 1, 0. So DI10 is on, DI11 is off. And I'm going to pick row 1 in my table by turning DI15 on and DI16 off. That will pick row 1. I'm going to now trigger an operation by turning the go bit on DI12, and we should see it positioned to 2003, so it should rotate clockwise. And off it goes. Looks like we're spinning away, and there we go, we have arrived. And you can see down there, position is 2003, so we did pick the right row in the table. Increments is a much bigger number because that's the actual number of increments it turned. I did hand calculate it and confirm it's correct. All right, so that works. So now let's go ahead and check the early exit conditions. I've turned my go bit off, and I'm going to pick row 2 in the table by turning DI15 off and DI16 on. I'm going to trigger my go bit, and I'm going to hit controller inhibit almost right away. So let's do that. Okay, as you can see, it started positioning. Now it's stopped. I'm going to turn DI12 off. And I'm going to turn controller inhibit back on. And we have gone back into the positioning state just like we should. Let me complete the operation. I'll trip DI12 again, and it will finish going to negative 391. And there, it arrives successfully. I'm going to now change back to row 1. I'm going to start it again, and I'll take enable away. And that worked fine. I'm going to leave DI12 on for a second, and you'll see what happens as soon as I give enable back. It'll go back into positioning, and it'll just resume that positioning operation. If you leave DI12 on, that's exactly what happens. And you can see, there it goes, and it's positioned. So that is legal operation. That's just the way it works. I'll turn off DI12 now, and I will change back to row 2. And we're now going to test the limit switch. I'm going to take off DI4. So here we go, position. Trip the limit switch. We have that and a fault. I'll turn the limit switch back on, and then I'll clear the fault by turning DI07 on and off. And that cleared the fault. I turned DI12 off, so it's not going to resume positioning, but I can just trip DI12 again, and it'll finish the positioning operation just fine. Okay. And of course, I could test the remaining limit switch, and if I were doing this in real life, I would test that as well. But I have tested it already, and it does work, so I won't waste your time making you watch it. So we've checked all the early exit conditions, except jumping out by changing modes, so we better test that as well. I'll do one more positioning operation. And I just changed mode, and it dropped out. That worked as well. It appears that all the early exit conditions work. Normal positioning works. It's going to the right rows in the table, and my status indicator is lighting up and going off correctly. I'm not sure if I mentioned this in some of the earlier ones, but it's been working correctly in all the parts of the program we've tested. I haven't actually showed it to you, but the light has been responding just as it's supposed to. So that is it. We have basically completed really the hardest part of our program, and that is positioning. It's also really the core of the program, what the program is all about. The last thing we do, of course, will be the teach mode. That's coming up next. Well, you're doing great, and we're now to our final piece of code that we're going to add to our existing IPOSplus program. This is the teach function. This function allows you to take wherever you happen to be, maybe you've jogged yourself there, for example, and put that in the 4th row of the positioning table. So this is kind of a programmable function. Here's what you need to do to complete the teach state function. First of all, again, you need to watch the go bit DI12 to turn on because that signals teaching begins. When that does go on, turn on the teach status indicator, which is DO17. That signals the PLC that teaching is happening. Take the current motor position and convert it to millimeters. Don't forget that. And then store it in the non-volatile location H9. That's the position location in the last row. Do not alter the speed or ramp. Those are hard-coded in there by the user using the all variables function. Of course, don't forget also you have to initiate a flash function with a memorize function. That tells the movie drive B to transfer the non-volatile memory locations into flash memory. As soon as that's complete, turn off the teach status indicator and wait for the go bit to go off. By the way, you do not have to worry about controller inhibit and enable and limit switches during that brief time that you're flashing memory. Just let it complete. Of course, afterwards, those signals are relevant, but don't worry about it during the teach operation. Now, you should stay in the teach operation. In theory, you could trip the go bit again. I don't know why you would, but it's possible, but don't actually exit. In order to exit the teach state, one of 4 things has to happen. Either you have to change to another mode, which is probably what happens normally, or you could have controller inhibit, removing enable, or a limit switch trip. If those things happen, or a mode change happens, then you should, of course, exit the teach state and re-enter the dispatcher state. All right, that's a pretty simple function. I don't think you'll find this one a big deal. But let me give you one handy tip here, and it's interestingly the same one I gave you for the last part of the project. Do a wait 100. That's 100 milliseconds or a tenth of a second after initiating the function that flashes the non-volatile memory. Takes about that amount of time to complete. So don't exit while that's happening. Do give it a wait, and that'll let it complete satisfactorily. Okay, well, go ahead and write your last piece of code for the table positioning program. Okay, well, let's compare code and see how we each approach this, so you can see how you did, and then that'll wrap up our program. Okay, well, this is our last piece of code, the teach state. So we're going to flesh out the teach function. Really isn't that complicated, so let's just take a quick look at it. Of course, as usual, I've expanded the conditions that exit out of the state and go back to dispatch. Not only does changing the mode take you out, but of course, control or inhibit, removing enable, tripping a limit switch, or a fault will bring you out as well. Now, assuming that none of those conditions has happened, the while loop will keep cycling, and we'll go in, and the first thing that will happen is we'll look at the go bit to see if it's time to teach. Now, as soon as the go bit turns on, we're ready to go into the teach cycle, which is very brief, so it's a little simpler than the positioning and referencing code. Of course, the first thing we do is we turn on the teach bit to signal the PLC that teaching has started. Then what we do is we insert the current motor position into the teach variable position. That's variable H9, but of course we've given it the name POS3. Now notice what we do. We take the system variable actPOSmot, which is the motor's current position. We multiply it by 100. That gives it 2 pseudo-decimal places. And then we divide it by our computed position scale. That converts it from increments back to millimeters and puts it in the right location. Then, of course, we trigger the memorize function, which takes the information in the non-volatile memory locations and flashes them into flash memory. We do that wait 100 to be sure the flash operation is complete. Then we turn off the teach bit to indicate that we're finished teaching. So what will happen is the light will just flash, actually, because this happens pretty fast. And then finally, we wait for the go bit to turn off or one of the other early exit conditions to happen. Now, if the go bit goes off, we stay in the outer while loop, so we could actually do a teach again if we want. It would teach the exact same position, so it would be kind of pointless. But we don't actually exit the current state. To exit the current state, we either have to change the mode bits to something else, or one of the early exit conditions like control or inhibit, enable, limit switch, or fault. As soon as that happens, of course, we go back to the dispatch state. So there we go. Pretty simple code. Let's go ahead and see if it works. Of course, we'll compile it and run it. The first thing we need to do is position our drive to some random location and then program it into the H9 location and check it out with the All Variables window. So what I'm going to do is really simple. I have my control box. The first thing I'm going to do is go to location 0. That is currently stored in the teach position. So that's kind of a home position at the moment. As soon as it arrives, we know where it's starting. And what I'm going to do then is jog it away from that location and then program it. All right, of course, we have now arrived at 0, so I'm going to put my control box into jog mode, and I'm going to turn on clockwise jogging for just a couple seconds. And stop it, and now I'm going to teach that position. So I'm going to switch to my teach mode by turning DI10 and DI11 both on. I'm going to take DI12, the go bit, and just turn it on, and hopefully I'll see DO17 flash, which I did. I'll turn the go bit off, and now I'm going to go to my All Variables window and see if there's something different in variable H9, and there is indeed 926. So that is presumably the location that I jogged to. Now, if I want to confirm that, I could manually calculate from active motor position this value. And I'll just remind you that the system variables are shown in red. And I'll find active motor position right here. It's H511. And it says that the motor's current position is 102,730 increments. So if I multiply that by 100 and divide by my scale factor, that should in fact give me the value that is currently residing in H9. And I have confirmed it, and it is correct. So it is clear that this code is now working, and with that, we now have a complete table positioning program. Good work. Well, congratulations. You have completed the senior project successfully. This is the end of session number 12. Good job. Now, I give you an option at this point. If you wish, you can end the course right here. This completes the basic understanding of IPOS. However, there are 2 more sessions, session 13 and 14. You could consider these kind of graduate school projects. These get into a few advanced topics that are very handy to know, so I would urge you, if you've gotten this far, get a little more coffee and complete the last 2 sessions. But if you feel like you're just programmed out and utterly exhausted, you are welcome to stop here and complete the course. But I really suggest, if you can, go on to the last 2. You'll find them interesting, and then we'll do kind of a wrap-up at the end. So good job. Thank you for sticking with the class up to this point, and I really look forward to seeing a lot of you in the next session, session 13. Have a good day.